Problem 4.15. A fixed spherical shell, inner radius A, outer radius B, is made of a dielectric material with a frozen-in polarization given by the formula P of R is equal to K over R, R hat, where K is a constant and R is the distance from the center. Find the electric field in all three regions using two different methods. Method 1. Locate the bound charge and use Gauss's law to calculate the field it produces. Now, I am going to start off by saying we have seen problems like this before, and I am going to skip over the parts where I calculate the electric field inside A and outside B, because those are going to be zero. You can, if you want, do this, but the point of this problem is to show the disparity in how much work it takes to solve using these two different methods. So the middle region will suffice for that. So if we are talking about finding the electric field in the middle region, that is in the meat of the shell, Gauss's law says that the integral of E dot dA is equal to the total charge inside our Gaussian shell. There are two sources of bound charge in our Gaussian shell. There is the bound volume charge, which is the negative divergence of the polarization, and there is the bound surface charge on the inner surface, which at the distance A, which is the distance of the inner surface, is negative K over A. It is negative because the polarization points out, but the normal direction away from our region is inward. So E dot dA is equal to total charge enclosed. Now, since we are dealing with a spherical Gaussian shell, and since this problem does have enough spherical symmetry that, again, we have done this many times before, I'm just going to go ahead and say that this side integrates to 4 pi r squared times the radial component of electric field as a function of r. I am also going to say that, again, because of the spherical symmetry, this volume integral can become a linear integral if we pull out a 4 pi to represent the angle integral, and we leave in an r squared pre-integration. So this becomes 4 pi over epsilon naught times the integral from A to R from the inner surface to our location of interest, negative K over R squared, that's the bound charge density, times R squared, that's from the volume integral of a sphere, dr. Plus, this is the total charge enclosed on the inner sphere. The charge density is negative K over A. I multiply that by 4 pi times A squared, which is the inner surface area. Now you'll notice r prime squared, these two will cancel out. And so this integral just becomes negative K dr, which means that it's the top minus the bottom. And this one, we have a 1 over A here and an A squared here. So one of those cancels and we're left with this. Now you'll probably notice that these two terms are the same, just with a different sign in front of them. So they will cancel, leaving this is the total charge enclosed in our Gaussian surface, in our Gaussian shell. We can go ahead and cancel out the 4 pi with this 4 pi, divide out this r squared, which cancels one of those r's, and we are left with the electric field at some distance away from the center of the sphere is equal to negative K over epsilon naught r, r hat. Now, method number 2. use Gauss's law, the Gauss's law form of electric displacement using the free charge. There is no free charge. Therefore, there is no electric displacement. That was easy. Next, we can go back to our definition of electric displacement. That's equation 4.21. Electric displacement field is equal to epsilon naught times electric field plus polarization. Since electric displacement field is 0, electric field is equal to negative polarization over epsilon naught. Polarization was again k over r hat. Electric field is negative k over epsilon naught r hat. Same electric field, both methods, and I think we can agree this method was easier.